Welcome to Describe Cisco SD-WAN Architecture. No conversation on wide area networking is complete without mentioning SD-WAN. Cisco recently, in the last few years, went out and bought a company called Viptela, and that became their SD-WAN product, which incidentally they call Cisco SD-WAN. SD-WAN is taking a lot of the principles of software-defined networking and applying them to our WAN space. So even some of the problems that we've talked about and some of the solutions that sort of work in the WAN area are made way better by deploying SD-WAN. So in this video series, we're going to focus on a high-level look at the architectural components, because if we're going to design something, we need to understand it first. So first of all, we'll understand it, and in the next video series, we'll look at how we design it. So with that, I will see you in the next video. Chances are, before you even opened up the Cisco ENSLD blueprint, you had heard of their software-defined wide area networking or SD-WAN solution. But we still need to figure out in a lot of cases what exactly that solution is all about. In this video, we're going to cover not only the goals of SD-WAN in general, not just Cisco, but everyone's goals in creating SD-WAN, and then specifically take a look at Cisco's solution to learn what its architecture consists of. Let's dive in. If you're working your way through the ENSLD course, then we just got done talking about traditional WAN environments and all of the problems that we have with them. For example, take this scenario here. Let's say we have an MPLS as our primary, and the DMVPN internet circuit, that's our backup circuit, our secondary link. And we know that with MPLS, we have to form routing relationships with the service provider, which is not only a security risk in and of itself, but then we're going to have routes showing up on the other side that are flagged as external. Meanwhile, we're going to be able to form native routing adjacencies between our locations via DMVPN, and those are internal routes. And while we are encrypting traffic going through the internet, that's great, we're not encrypting traffic going through MPLS, at least not natively. Furthermore, failover is a concern because as application traffic comes into our router, we have to choose which link we're going to send it out. And in most cases, we're not interested in sending application 1 out the link on the left and application 2 out the link on the right. That's very complicated from a routing perspective, especially when it comes to failover. Because if the MPLS circuit were to go down, we'd still want one to fail over to DMVPN and vice versa if the DMVPN circuit were to go down. As such, we will simply send all of our applications out the primary link and use the backup link only in the event of a failure, which results in inefficient use of those resources. Lastly, managing all of this. How exactly are we doing management? Well, in most cases, we're doing it via CLI. We're performing CLI changes on all of the different routers, so if one of our policies happens to change, that's going to require a lot of effort from a CLI perspective in order to push that policy out to all of our devices. So we have some goals in mind for ways that we want to try to fix our traditional wide area networking environments. First of all, the topology. We want to create and own our own topology. With traditional WAN, my topology looks very different depending on whether I'm going out MPLS circuits or DMVPN circuits. And furthermore, that results in complicated routing environments. So the idea of simplifying routing is absolutely a goal that we should have. I don't want to have to worry about sharing routes with my MPLS service provider anymore. And for that matter, forming adjacencies across a WAN, that's not always the most efficient way to go about sharing routes. So how can we simplify routing and on top of that, improve failover? As mentioned, we're pretty good with this concept of primary and secondary connections. We can send all of our traffic out one way, and if there's a problem, then we can redirect all of our traffic out the other circuit. But if we can simplify routing and improve failover, then we should be able to do what we call application routing, which is the example we gave down here, where application 1 gets routed out the left link, application 2 goes out the right, and again, because we've improved our failover processes and simplified our routing environment, well, now we can load balance across those links and fail over in the event of an emergency. Now, a big goal that we need to have, especially in the modern networking era, is to improve our security of our WAN environment. As we mentioned, we are encrypting traffic sometimes, not encrypting traffic other times, sharing routes with our service provider, that's a security risk. We need to greatly improve the security of this environment, to the point that this security needs to be foundational to our solution. And what I mean by that is it must be part of the solution from the beginning. I want this to be a check mark in my configuration policy rather than an entirely new protocol or an entirely new methodology that I have to layer on top of an existing solution. Now, what about management? We mentioned that management is a little bit of a disaster in traditional WANs, because not only am I doing CLI, I'm doing CLI to every single device in the environment. So I want to improve that by deploying centralized management. And furthermore, make it programmatic. For better or worse, CLI is not the most efficient way that I can configure these devices in the modern networking era. So give me REST APIs, give me netconf, but ultimately, just simplify and improve my management environment. Now, it's probably ambitious enough to have all of these goals in mind when we're talking about a new solution, but could we also add on lowering the cost of my WAN environment. Boy, if it wasn't ambitious before, it is certainly ambitious now, because to improve the WAN environment that much and yet lower the cost of the solution, is that even possible? But think about it for a moment. If I have simplified routing, an improved failover, and application routing, could I not deploy 2 separate internet circuits instead of MPLS? Internet circuits are so much cheaper than MPLS, they are simply less reliable. But if I have the ability to seamlessly fail over my applications back and forth between 2 separate internet circuits, well, maybe that's enough. Maybe that's good enough for my organization that I can start to cancel out some of my MPLS circuits. Certainly, at least in some organizations where we have 2 MPLS circuits, we could probably in those cases get that down to 1. So there is a way of lowering cost with an SD-WAN solution, and that would involve migrating traditional WAN circuits over to internet circuits and rely on the benefits of SD-WAN to cover us for the gaps that internet gives us. So these are some lofty goals that we have, but we can accomplish them primarily by delivering a consistent topology across our environment. We need to define some terms. First of all, we have the underlay concept. The underlay in an SD-WAN world is going to be the traditional WAN architectures, so MPLS and the internet and such. These are now going to become an underlay network, and we are going to build an overlay. We want this overlay to look the same, to be consistent, regardless of what's happening in the underlay. Again, whether I have 2 internet circuits or an MPLS and an internet, or maybe 3 internets or 3 MPLSs, I want this topology to look the same regardless of what the underlay looks like. And the way we're going to accomplish this is by building tunnels. Whenever we're talking about an overlay, usually that involves tunnels of some kind. And in this case, these tunnels are going to be IPsec. Now right away, IPsec tells us that we are encrypting this traffic. So we can already check off security from our list of goals. Furthermore, we can now control the routing environment. Because we are routing through these tunnels, we no longer need to form routing adjacencies with our MPLS service provider. So that further improves the security as well as gives us that control over the routing environment. Now that said, even though we might say, well, this is great, this looks like DMVPN will just form native routing adjacencies on both sides, that's not exactly how we want to go about doing this. Because if we have a WAN environment with dozens or hundreds or thousands of routers, forming that many native routing adjacencies is not going to scale. So instead, we want a separate device, a control plane device that's going to tell all of these routers how to reach one another and how to reach the networks that exist behind them. This is all to improve the scalability of our environment. And lastly, remember, we want to manage all of this from a centralized point, and so we want to deploy a software package that's going to manage all of these devices for us. So if we make a policy change here, then it gets automatically pushed out. We don't have to worry about logging into every single device in our WAN environment via the CLI. So at a high level, this is how the Cisco SD-WAN architecture comes together, and Cisco breaks this down for us into 4 separate planes. We have the data plane, the control plane, those 2 planes should sound familiar. We also have the management plane and the orchestration plane. We've had this concept of a management plane around for a little while, but orchestration plane is unique to the SD-WAN infrastructure, and so we're going to be talking about that in more detail later on in this skill. For now, staying at a high level, we need to understand that these 4 different planes each map to a different component in the Cisco SD-WAN architecture. At the data plane, for example, we have the V-edge and we have the C-edge. The little v is going to stand for Viptela, and as mentioned in the intro for this skill, Cisco acquired this solution from a company named Viptela. So that little v represents Viptela, meaning that the V-edges are actually routers that came along with that acquisition. However, as you can imagine, Cisco has integrated all of this functionality into their own routers. That's what the little c is for, so we'll be talking about V-edges and C-edges in the very next video. Now at the control plane, this device that we mentioned, this is going to be known as the vSmart. The vSmart is responsible for propagating routing information, so again, we don't have to have routing adjacencies across our WAN circuits. Now over here we mentioned centralized management, and as you can imagine, that's part of the management plane. The device that's central to the management plane would be the vManage, appropriately named. And lastly, we have this concept of orchestration. We haven't really gone into those details yet. However, that involves a device that we call the vBond. It is the glue that holds all of this together, and so it's appropriately named as well, the vBond. So in order to best understand the SD-WAN architecture, we need to take a closer look at each one of these planes, as well as the component that exists within each one. So the primary takeaway from this conversation is to understand that we have a lot of problems with traditional WANs, and that SD-WAN is designed to solve all of those problems as best we can. So remember, we have that list of goals that we're trying to accomplish and ways that we want to improve our life from a WAN perspective. Second of all, the WAN topology, as we described, it's going to be created from an overlay of IPsec tunnels. And right away we hear IPsec and we know, okay, that's going to solve some security problems. It's even going to solve some routing problems for us. But beyond that, it's going to give us a whole lot better foundation laid for us to fix all of the problems that we want to fix. Lastly, when we think about Cisco's SD-WAN solution, from a high level, we have 4 different planes of operation. We have the control plane, the data plane, the management plane, and the orchestration plane. Each plane has components associated with it, and we're going to be covering those once again in more detail over the course of the next few videos. I hope this has been informative for you. I'd like to thank you for viewing. The first of the 4 planes we're going to talk about is the data plane. Back when Cisco acquired Viptela, they acquired with them a bunch of hardware. It was called the vEdge, an actual routing platform that Cisco didn't develop. And at first, if we were deploying Cisco SD-WAN, it all had to be on these vEdges. Fortunately, Cisco eventually was able to migrate that functionality into their own routers. So in this video, we're going to take a look at both the vEdge and the cEdge, as well as how the data plane comes together in a Cisco SD-WAN architecture. Let's take a look. When we're talking about the data plane of the SD-WAN architecture, we're really talking about the routers that we're deploying to the WAN edge. In a lot of cases, this is going to be actual hardware, meaning that it's a physical device that we install into our network. Think about Cisco routers. For example, we have ISRs and ASRs and such. But at the same time, we might end up with a virtual environment, with a virtual router in there. And that virtual router might even bring in WAN circuits. This is perfectly common when deploying public cloud infrastructures and bringing potentially an MPLS circuit into my cloud space. But at this point, this router needs to be a software router, otherwise known as a virtual router. And it doesn't matter whether it's a physical or virtual router, either way I'm going to form those IPsec tunnels among the different routers in my infrastructure. So again, I might be forming IPsec tunnels out to the public cloud for the sake of connecting to my virtual router. Furthermore, I want to create these IPsec tunnels on a per WAN basis. So that's going to result in even more tunnels. This is why it's so important that we have a management plane to this SD-WAN fabric that manages all of these tunnels for us. Now these tunnels, as we've mentioned, are going to be IPsec. However, we do have the option of deploying generic routing encapsulation or Cisco's GRE protocol. It's just not going to be encrypted. And so in most cases, we are going to select IPsec as our tunnel mechanism of choice. Now something we need to understand about SD-WAN is that if we are running, let's say, EIGRP in this environment, well, in traditional WANs, if I've got IPsec tunnels, I would be forming EIGRP neighborships across those tunnels. Think about DMVPN, for example. However, in an SD-WAN space, I am not going to form EIGRP relationships with one another. Instead, I'm going to rely on that vSmart controller to exchange routes among the different edge devices. And we'll be talking about that vSmart in more detail in the next video. Now, I mentioned in the intro that we have 2 different choices when it comes to the routers that we deploy into an SD-WAN environment. The first choice is going to be the vEdge. The vEdge at this point is pretty much considered legacy. The little v in all of these devices, vSmart, vEdge, vManage, that all stands for Viptela. Viptela was the company that was acquired by Cisco that gave them this architecture. And so we're talking about routers that you and I as Cisco engineers might never have deployed otherwise. There are 4 main lines of vEdges. We had the 100s, which are for small businesses. Then we also had the 1000s, the 2000s, and the biggest hardware piece that they had was the 5000s. They also had a virtual solution in the vEdge cloud that could go into, well, our cloud environments or any virtual infrastructure. However, several of these models have already gone end of sale. We can no longer order them from Cisco because Cisco doesn't want us to buy vEdges anymore. Instead, Cisco wants us to purchase cEdge devices. Now, cEdge devices, which are occasionally referred to as XE SD-WAN edge devices as well, these are Cisco routers that are running iOS XE. Cisco made the migration many years ago from traditional iOS to iOS XE, where iOS is now a process that runs on a Linux platform. These now run on a single image that includes both SD-WAN and non-SD-WAN modes of operation. This wasn't always the case. When Cisco first put out cEdges, we had 2 different images that we needed to manage, but fortunately now it's just a single one. That said, we have 2 different modes of operation. We have SD-WAN mode of operation, and we have iOS mode. iOS mode would be your traditional CLI managing config-t type of interface that we don't get with SD-WAN. We don't need it anymore because vManage is going to manage it in SD-WAN mode. So we can switch back and forth, so to speak, between the 2 images. However, as you can imagine, that's not going to be a very common thing to switch back and forth. More often what's going to happen is we're going to start with the iOS version, and once we're ready, we're going to upgrade to SD-WAN. I suppose there could be a situation where we're removing SD-WAN from an environment, and in that case we could move from SD-WAN back to iOS. But anytime we migrate, we're losing all of the configuration information, so just keep that in mind. It's not simply a config-t enable iOS mode or anything like that. We are fundamentally changing the way this router behaves, and so we can't just migrate a configuration from one to the other. Now, when I think of Cisco routers and iOS XE platforms, I'm going to think of platforms such as the ISR 1K line, as well as the 4K line. These routers can be implemented as C-Edge devices. Additionally, we can run ASR 1Ks in Cisco SD-WAN. And from a virtual perspective, we can run the CSR 1000V. Now, up until late 2020, these were the only devices that could be used in a Cisco SD-WAN environment. However, Cisco now has the Catalyst 8000 line of edge platforms. They don't call them routers, they call them edge platforms, and the reason for that is because they're bringing together all kinds of functionality, like ISR voice and security and server functionality, and ASR performance, as well as the virtual line of routers. They're bringing all of that together into the Catalyst 8000s. And so they didn't want to simply call them routers. Instead, they have called them the Cisco Catalyst 8000 Edge Platforms. Now, the 8000s have routers, again, like ISRs and ASRs, but they also have the 8000V. So they have a virtual router as well. So when it comes to deploying data plane devices, again, we're going to want to deploy C-Edges. However, if we are an organization that's been running Cisco SD-WAN for a while, and we have a bunch of Viptela V-Edges out in the environment, then it might make sense to acquire some more V-Edges just to simplify the management of that infrastructure. That's a business decision that we're going to have to make. However, we are able to go out and purchase C-Edges from the beginning because we can intermix V-Edges and C-Edges in a Cisco SD-WAN architecture. However, there's a caveat to that, and we can only intermix them if they're at different sites. If, for example, we have a V-Edge up here in the top left, and that's one site, and we have a C-Edge down here at the bottom, and that's a different site, that's a supported architecture. However, if these two routers at the top are at the same site, we could not deploy a V-Edge on the left and a C-Edge on the right. That is not supported because the way V-Edge and C-Edge handle some local protocols is very different, which is why it's an unsupported solution, and if we want a C-Edge running, well, we will have to replace that V-Edge with a different C-Edge device. So there's a lot of information that we just covered. However, here are some of the main points that we need to keep in mind. First of all, the data plane edge devices, they can be either hardware or software, so we can support physical routers and we can support routers up in the cloud. Data plane devices then will form IPsec or GRE tunnels to one another. They do not form routing adjacencies. They simply are going to form these tunnels, and we will rely on the vSmart, again, we'll cover that in the next video, for the control plane information. Next, we have those V-Edges and the C-Edges. The V-Edges were part of the Viptela acquisition. They are considered legacy at this point. However, as we saw, there are many different hardware and software models that they supported. Now, however, we have the C-Edge. And the C-Edge is built on iOS XE, Cisco's go-to iOS routing platform. And so we can build that now on ISRs and ASRs and the new Catalyst 8000s. I hope this has been informative for you, and I'd like to thank you for viewing. It might seem strange at first that we're not forming routing adjacencies directly across the SD-WAN. Instead, we are relying on the vSmart controller to do all of the routing exchanges for us. In this video, we're going to explore how exactly the vSmart controller does that, which at the center of it all is a very important protocol known as the Overlay Management Protocol, or OMP. Let's take a look. We're going to find that all of these devices have an icon of some kind. We already drew the V-Edge and the C-Edge. They're simply a router icon. However, now we're going to talk about the vSmart. And the vSmart has this atomic-looking symbol, I suppose, to make it look like it's really smart. The vSmart is going to sit out of band of the rest of the network. So while our edge devices are all forming connections to one another through the WAN space, forming these IPsec tunnels to one another, the vSmart is going to sit outside of the traffic path, forming TLS or DTLS connections to the edge devices. And as mentioned in the intro, the protocol that we are going to run across these connections is going to be OMP, the Overlay Management Protocol. OMP is pretty interesting. It's very similar to BGP in the way that it operates, in that it's a TCP-based protocol, and it's more of what I'd call an information carrying protocol rather than exchanging routes directly. So yes, we are exchanging routes and masks, but we're also going to carry attributes as part of every route. The vSmart is also going to operate sort of like a BGP route reflector. And no worries if you haven't studied BGP, because all that means is that we're going to learn the routes and the subnets that are attached to a particular edge device, learning it via this OMP relationship, and then we're going to push that down to the other routers, also again via OMP. We're going to get to enforce policy that we set, like for example, maybe we don't want a particular path to be used by a certain application, and we're going to include that in those attributes. This is how different edge devices understand how they're supposed to route traffic in the SD-WAN space. Now if you're wondering where this policy comes from, well, the policy is coming from vManage. vManage is where we're going to configure all of our policies and be the centralized point of all of our management, and that's going to push that information to the vSmart controller for us. And we'll be talking about that in more detail in the next video. Now when we're doing our network designs, we want to consider the fact that the vSmart can scale. And what I mean by that is we can deploy multiple vSmarts depending on the size of our network. Specifically, each vSmart can support up to 2,700 OMP relationships, and each vSmart can support up to 256,000 routes. Now that said, because we're going to form OMP relationships with other devices like other vSmart controllers and the vBonds and such, Cisco recommends us planning on roughly one vSmart controller for every 2,000 edge devices in the network. And for the sake of redundancy, we recommend a minimum of 2 vSmart controllers. So when we're looking at the control plane of the SD-WAN environment, it is all about the vSmart controller. The vSmart controller is a virtual appliance, and we can deploy several of them depending on the scale that we need, keeping in mind we want at least 2 vSmart controllers for redundancy. Second of all, the vSmart is going to receive our information from vManage. So we're going to be talking about in the next video all of the ways that we use vManage, and that's where we're going to define our policy. And as we saw, vSmart rather, is going to turn around and it's going to advertise routes and learn routes via OMP. OMP is that BGP-like protocol, and it's really what we're running all of our SD-WAN on from a routing perspective. The OMP we can use to enforce policy that we've defined in vManage, and we push that out to our edges via this protocol. I hope this has been informative for you, and I'd like to thank you for viewing. Next up is the management plane, and at the center of it is the vManage virtual appliance. In this video, we're going to cover how exactly we use vManage in an SD-WAN infrastructure, and ultimately how it completely and fundamentally changes the way that we're going to manage this network relative to traditional environments. Let's take a look. So our SD-WAN environment's really starting to come together. We have our edge devices, and they're forming IPsec tunnels to one another. Then we have our vSmart controller. Our vSmart controller is forming OMP relationships with each edge device in our network. But now we have the question of, what am I supposed to do as the network admin? I'm ready to log in and configure this network, but do I log into the edge devices? Do I log into the vSmart controller? And by now you've probably caught on to the fact that we are not logging into any of these devices. Instead, we are logging in to the vManage controller, whose icon looks a little something like this. Most administrators of a Cisco SD-WAN environment are going to take advantage of the graphical user interface, or the GUI, that's tied to the vManage appliance. But here's what's interesting as I move our diagram around a little bit. What I'm really doing is I'm using the graphical user interface, and that GUI is actually going to make REST API calls to the vManage controller itself. And if that's how I want to configure vManage and I'm never planning to do anything else, then that's great. I can effectively use the web GUI as the network admin for this environment. If, however, I want to take advantage of those REST APIs, well, I can simply call those directly via Python or Postman or whatever methodology I want to use in order to call those REST APIs. So regardless of whether I'm using the GUI or I'm using a programmatic method, either way, those REST APIs are the only way that we can make actual configuration changes to the vManage appliance. Now, all that said, there's always rules and exceptions, and there is an exception that we need to be aware of, and that is, yes, there is some amount of troubleshooting that we will do via the CLI by logging into the edge devices. The reality is that even with Cisco SD-WAN, we are unable to get 100% away from the CLI, and so there will be scenarios where we'll need to use the CLI in order to bring a device online or to troubleshoot a particular issue. But for the most part, our goal is to rely entirely on the GUI or the REST API calls. That is how Cisco would prefer us to manage an SD-WAN infrastructure. Now, just like with vSmart, vManage is going to form connections out to all of the different devices, including vSmart, by the way. And the reason for this is as we make configuration changes on vManage itself, we want to push those changes down to the devices appropriately. And vManage is going to use a protocol called netconf in order to accomplish this. Netconf is a programmatic way of configuring devices remotely, and it's going to use the structured markup language XML and push that over SSH connections. So we are securely and programmatically configuring our devices from the vManage appliance. Any changes that would be locally significant to a particular router are going to be pushed directly to that edge device. However, anything that's global in nature is going to be pushed out to the vSmarts, and the vSmarts will enforce that policy via OMP attributes. Now, the way we scale vManage is a little bit different than with vSmart. Specifically, we are going to cluster our vManage devices together rather than having them all be in an active-active state. We're simply going to cluster active vManages together and ideally have a second cluster as a backup. So our clusters are actually going to be in an active and standby state. Now we are able to cluster up to 6 vManages at once, and each vManage can support up to 2,000 edge devices. So even though it is a little bit different how we scale this out relative to vSmarts, we are still supporting the same number of edge devices. The key here being that if we, for example, need to support 6,000 edge devices, well, that would in theory be 3 different vManages. However, that would be 3 vManages per cluster. So we need 3 vManages both on the primary side as well as on the standby. Just like with the vSmart controllers, these are virtual appliances and they can only be deployed virtually. So they could be deployed in a cloud, they could be deployed into a virtualized environment. But either way, we want to make sure that we're deploying the correct amount of vManages for the size of our environment. So in review, one of the biggest changes that we need to make as network admins is recognizing how we're going to manage this environment. We are either going to use the graphical user interface of vManage, which incidentally on the back end is tying into REST APIs, or we can access those REST APIs directly. Second of all, vManage is going to leverage netconf as a programmatic language to push those configurations and those policies down to the edge devices as well as the vSmart controllers. Lastly, the vManages themselves are virtual appliances, and we want to scale accordingly. Remember that they're not all active-active. We have an active cluster and a standby cluster, so we need to cluster the appropriate number of vManages together, keeping in mind we'll need to do that as well for the standby cluster for redundancy. I hope this has been informative for you, and I'd like to thank you for viewing. It's time to tackle the orchestration plane. After covering the control and the data and the management planes, this one's going to sound a little bit different to us, because there is no such thing as an orchestration plane in traditional networks. Well, in the SD-WAN framework, we are going to need a little bit of extra help connecting all of these different devices to each other. And that's exactly what the orchestration plane is intended to do. And at the heart of it is the vBond appliance. Let's take a look. The vBond appliance is going to be represented by a symbol that is a circle with a couple of lines through it like this. Just like the other controllers, the vBond appliance is going to be virtual, meaning we can deploy it into a private cloud space or into the public cloud. It can support up to 1,500 different connections, and Cisco estimates that we should plan on one vBond per 2,000 edge devices. Now I might be looking at that and saying, well, wait a second, we can only support 1,500 connections. Well, how are we supporting 2,000 different devices? And we'll see why here in just a moment. Now, the reason we have an orchestration plane and a vBond controller is for the scenario where we are adding a new router into our SD-WAN environment. Let's say this router has just come online, we've connected it up to our service provider, but now it needs to know where the vSmart is, and where vManage is, and where the other edge devices are that we need to form tunnels to. Well, rather than trying to load all of that information onto the edge device that's coming online, instead we only add one piece of information, which is where the vBond controller is. And it's going to reach out and form a DTLS connection to that vBond controller. Now the vBond controller is going to do a couple of things here. First of all, very importantly, it's going to authenticate this router. Are you allowed into our SD-WAN environment? Security is baked into the foundation of SD-WAN, and so this is an opportunity for us to say, wait a second, you're not a router that's allowed to be in our network. And so we authenticate it to be sure that this is something that we are intentionally bringing online and not a rogue device that either is accidentally or maliciously trying to join our SD-WAN network. Once it's been authenticated, the vBond controller is going to pass all of the needed information back to the edge device. This allows the edge device to form those connections we talked about in the previous videos, such as TLS or DTLS connections up to vSmart and vManage. At this point, my edge device is able to form an OMP relationship with the vSmart controllers, and it's able to form those IPsec tunnels out to the remote edges. At this point, my connectivity has been established, and I don't really need this connection to the vBond controller anymore. So importantly, as part of this process, I tear down this DTLS connection. This is why the vBond controller is able to support more devices than connections itself, because the connections are temporary. They don't need to be up any longer than forming the initial connections to the other controllers and edge devices. Now there is one other thing that the vBond is responsible for, which is NAT traversal. In some situations, especially when the internet is involved, we might find ourselves behind network address translation. What that means is I have a private IP address on my router and I'm trying to form a connection out to another router that might be in the same situation. It might be NATed to the service provider, meaning I have a private IP address up here. In a situation where I have two different devices that they're trying to communicate with each other, but they're both behind NAT, we have a problem because I can come through my own NAT, but I can't get through the other side. Likewise, the remote router is able to get through their NAT, but can't get through mine. Fortunately, there is a workaround for this, and it's known as NAT punch-through or NAT traversal. What we're going to do is we're essentially going to send traffic to one another at roughly the same time. If we coordinate this well, the traffic is going to be able to pass through the holes, so to speak, that we opened in our own NATs. And since this does require coordination, we are going to rely on the vBond to orchestrate this process. Now, there's an important rule for the device that's performing this coordination. The device that's out here telling these two devices when to send traffic to each other cannot be behind port address translation. In other words, it's not really supposed to be behind NAT at all. However, we can make it work if it's a one-to-one NAT. Well, since that device is our vBond controller, we need to apply those rules to it, meaning that if it is behind NAT, that it must be a one-to-one NAT configuration. meaning that it has its own reserved public IP address. We are not allowed to use port address translation or PAT on the vBond appliance. So when we step back and take a look at the orchestration plane and the vBond specifically, we see that the vBond is appropriately named. It's the glue that holds all of this together. So when we think about what we need to remember about the vBond, first of all, it's a virtual appliance, just like the other controllers, and we looked at how it can scale as well. Second of all, vBond performs edge authentication. When that device fires up, we want security at that point. We want to make sure rogue devices aren't trying to attach into our SD-WAN environment. And so the vBond is going to do that, and then it will connect our edge device to the controllers, which will allow it to connect to the other edge devices. And lastly, that other very important functionality that vBond has is NAT traversal. In some cases, we're going to need some help for these edge devices to be able to form tunnels with one another. And in the cases where they're both behind NATs, the vBond is going to help us get there. I hope this has been informative for you, and I'd like to thank you for viewing. The topic of SD-WAN is huge, to the point that we have an entire course on CBT Nuggets dedicated to it, which is incidentally based on an exam that Cisco has dedicated to it. That would be the ENSLD exam. That said, there are a lot of concepts that we're not covering as part of this course, because this course is focused on some foundational principles plus design elements, which we're going to be covering in the next skill. That said, we do need to understand a few more concepts about SD-WAN before we move on. In this video, we're going to cover VPNs, colors, and TLOCs, three very important concepts within the world of SD-WAN that will help us with our designs. Let's dive in. First, we need to tackle the concept of a virtual private network, or VPN, within the context of SD-WAN. I don't know about you, but when I think about VPN, I think about tunnels and encapsulations and security and extensions between networks. But that's not what a VPN is in SD-WAN. A VPN is really more like a virtual routing and forwarding instance, or a VRF. It's a network segmentation that allows for multi-tenancy in a layer 3 infrastructure. For many of us working for organizations, we don't have to worry a whole lot about VRFs, other than maybe a management VRF here and there. But for service providers, this is a very important concept. So here's how this works. Let's say we have two routers in this infrastructure, but these routers belong to service providers, and they have different organizations, let's call them organizations A and B, hanging off of them. Likewise, at a different site, we have organizations A and B hanging off of that router. The goal here is that organization A will be able to communicate with its own network and its own devices across this shared infrastructure, that network B will be able to do the same, and that they will not be able to cross one another in the path. If we can get our wires crossed here and organization A can reach organization B's network, or vice versa, well, that's no good, and we need to prevent that from happening. So the way we handle this in SD-WAN is by assigning these interfaces into specific VPNs. Let's call this one VPN 10, and this one here on the right, VPN 20. When traffic comes into one of these interfaces, it's going to get tagged with a particular VPN. Now we'll recall that we have an IPsec tunnel formed between these two routers, and so we need to make sure that we can put both of those VPNs into the same IPsec tunnel. And that's exactly what's going to happen. Our one IPsec tunnel is capable of carrying all the different VPNs that we need to support in our infrastructure. Now, all this is great, but what if I'm an organization who doesn't need VPNs? Do I really need to understand this? And you can imagine my answer is going to be yes, we do still need to understand the concepts. But beyond that, we need to understand that we are using VPNs even in an infrastructure that doesn't have multi-tenancy. Specifically, we have VPN 0 that is reserved for the underlay. In other words, these physical connections belong to VPN 0. Likewise, we have VPN 512 that's reserved for management. So there are two things to keep in mind here. First of all, even if we're not multi-tenant, we're going to be using these VPNs in our configurations. Second of all, if we are multi-tenant, these VPN values are reserved. We cannot use 0 or 512 in our infrastructure. Other than that, the full range of VPNs will be 0 to 65,530. Yeah, it's a bit odd that they didn't go to 535, but hey, this is what Cisco gives us. And so we can use any of these VPNs other than 0 or 512. So really our range is going to be 1 to 511, and then 513 to 65,530. Well, that's it for VPNs. Next up is the concept of colors. Now, when we're explaining SD-WAN and using WAN topology drawings, in a lot of cases, we like to just draw a single WAN cloud for simplicity's sake. However, in the real world, in most cases, we're going to have redundant WAN circuits going to all of our different sites. In fact, if we don't have redundant WAN circuits, then the value of SD-WAN goes down pretty significantly. One of SD-WAN's biggest advantages is that it can help us manage multiple WAN circuits, maybe 2 circuits or possibly even 3 or 4 or more. As such, we need a way to track the different WAN circuits within the SD-WAN configuration, and that is the concept of color. Colors are going to be strings that we use to assign descriptions to a particular WAN service provider. In other words, let's say that our service provider on the left is MPLS, the provider on the right is, maybe we're using cellular, let's call it 3G. And so we can assign strings to these. We can assign the string on the left to be MPLS and the string on the right to be 3G. These are predefined strings within the SD-WAN configuration, so in vManage, we'll use a dropdown to select the best color description that we can for a particular service. Some of the examples, besides what we've just given, like 3G and MPLS and Biz Internet, are going to be literal colors like red and green and blue, and also different quality metrics like bronze and silver and gold. The color is a relatively arbitrary choice that we as the admins are going to assign to these different circuits. We're going to use the colors to inform the edge device what their circuits belong to. So for example, we tell this router that the circuit on the left is part of the MPLS color, and the circuit on the right, well, that's part of the 3G color. And that's really it when it comes to colors. That's about all there is to it, other than that colors are used extensively by the concept of a transport locator or a T-lock. We can think of T-locks as the connection points for routers to make to one another. For example, on this router up here, I might have a T-lock that belongs to the color MPLS, and then I'll have another T-lock that represents the 3G circuit. Well, likewise on the bottom, I'm going to have two different T-locks for the two different circuits as well. Now, a T-lock is more than just a color, however. There's actually a 3-tuple of information that's included inside the T-lock. First of all is the system IP of the router. Yeah, we can't have the same T-lock on two different routers, and so the system IP is going to tell us which router it belongs to. Second of all is the color. That's an important concept as well. We need to know which circuit we're attaching to. And lastly, we have the encapsulation type. Because remember, we can choose between IPsec and GRE, and so as part of this connection type, we need to know which type of connection we're going to use. Our edge devices are going to use these T-locks to form the appropriate tunnels to one another. So for example, on the MPLS side, I would form an IPsec tunnel between the MPLS T-lock on one router and the MPLS T-lock on the other. Likewise, I'll do the same thing on the 3G side. However, one of the most interesting parts about the T-lock is what it doesn't include. We note that it doesn't include a physical IP address. There's no way for me to know based on the T-lock alone how to actually reach out and connect to that device. Instead, we rely on that overlay management protocol, or OMP, to give us that information. It's going to tell us, hey, if you're trying to connect to this T-lock, use this physical IP address. And that's how we're able to form our tunnels. Now, by default, an edge device, like we have down here at the bottom, is going to want to form connections to every T-lock on the remote router from every one of my own T-locks. In other words, the goal is going to be to do this, to form a full mesh of adjacency among my different T-locks. The problem with this is that in our case here, where we have MPLS on the left and 3G on the right, well, there's no way for me to connect through the MPLS circuit and attach to the other side via 3G. It's simply not going to work out that way. We can't form the T-lock through the router, go through the router and connect to the 3G interface. We could certainly ping that interface, but we can't form an IPsec tunnel that way. As a result, in this topology, we would end up with this scenario here, where we really only have two separate IPsec tunnels between these two routers. However, what if this wasn't an MPLS circuit? What if this was an internet circuit and we're forming our IPsec tunnels across it? Well, the 3G is basically internet, so whether it's 3G or another different type of internet circuit, either way, these two clouds are actually connected because it's all one global internet. At this point, there's nothing stopping me from forming a T-lock of one color to the T-lock of the other color. So in this scenario, we would end up with a full mesh of IPsec tunnels. That said, this is behavior that we can disable from a management perspective, but if we are designing our SD-WAN environments, then we need to understand the default behavior of T-locks, which is to form IPsec tunnels with every other T-lock that's possible on the remote router. Alright, so as you can tell, T-locks are a pretty complicated subject. In fact, if you're watching this and trying to figure out a little bit of how it all works, just understand that we don't need to know this in depth for the ENSLD exam. If you want to know more about T-locks for real-world network designs, make sure to go watch the ENSDWI section of our SD-WAN course that will tell us exactly how T-locks work, and OMP facilitates all of that with T-lock routes and OMP routes, and it's a lot of fun. It's very fascinating, but for the sake of the ENSLD, really what we need to know is this. First of all, the concept of a VPN is equated with a VRF. A VRF is simply a layer 3 segmentation between different layer 3 domains, and that's what a VPN is as well. It helps us with multi-tenancy. Second of all, colors represent WAN circuits. They're basically descriptions. It tells the routers which circuit I'm actually attaching to. We don't want to just base that on an IP address, for example. We want to explicitly tell it that this is our MPLS circuit. Lastly, the T-lock Again, just boil it down to this. It's a 3-tuple of information. It includes the system IP, it includes the color, and it includes the encapsulation type. And we use TLOCs to help us form those IPsec tunnels to one another. Even though the TLOC is missing the connectivity information, we get that from OMP, so we just use the TLOCs to tell us which IPsec tunnels that we need to form. I hope this has been informative for you, and I'd like to thank you for viewing. In addition to all of the advantages that we've talked about already with how superior SD-WAN is to traditional WAN infrastructures, there are still some features and benefits that we have yet to cover. In this video, we're going to take a look at some of those, including onboarding and security and such. So let's take a look. A great benefit to software-defined WANs is going to be the ability for us to automatically do onboarding of new edge devices. And there are two different methodologies for this. First of all, we have zero-touch provisioning. This is the old way of doing things. This was Viptela's methodology, and so this would apply to vEdges in our environment. However, Cisco already has a zero-touch provisioning methodology that they call Plug-and-Play Connect, or PNP. So this will apply to the C-Edge devices in our SD-WAN environment. The best part about this is that in traditional architectures, I would have to take a new router. Let's say we're bringing up a new site, we've got a new router, and I would have to configure that as the network admin. I'd maybe have to even go on site to get this spun up. However, I have to do neither of those things with automatic provisioning. Instead, I'm going to simply send this device out to the location that's going to, and maybe a local manager or somebody can plug it in for me. In fact, that's all we need. We just need power and we need networking. So if we can walk through our user to plug this in for us and get it connected to the WAN circuits like this, well, it will automatically reach out to the ZTP or PNP servers in the cloud, and it will download the configuration for us. This is going to save us a lot of time when it comes to onboarding and provisioning new sites. Now, another key advantage to SD-WAN is going to be this concept of integrated security. With traditional network infrastructures, a lot of times we're just deploying security as best we can, layering it on top of technology that wasn't built with it from the ground up. But not so with SD-WAN. We have security built in, and in a lot of ways, we don't even have to configure it. It's just part of the system. For example, SD-WAN uses what we call a zero trust model. This means that when a new device is going to come online, we're not automatically going to assume that that device belongs to our network. We might have accidentally configured the wrong router, or somebody maliciously might be trying to join our infrastructure. And so what we want to do is we want to, first of all, check it against a whitelist that we have configured on our vManage. And then second of all, we're going to use certificates to make sure that it's a valid device. Is it authentically a Viptela or a Cisco router, virtual or physical? It doesn't matter. Either way, we want those certificates to prove that you are who you say you are. So then when you connect up, we know for sure that this is a secure deployment. Furthermore, we've got the ability with Cisco to deploy all of our other security mechanisms. So with Viptela, again, they were just an SD-WAN provider, but Cisco has all kinds of security platforms that we can now integrate into this solution. For example, we think about their IPS and IDS systems. We can also think about Cisco Umbrella. Umbrella is traditionally a DNS tool that gives us security at the DNS layer, but also we can use this for URL filtering. And lastly, we think about advanced malware protection. That would be Cisco's anti-malware practice. So we can deploy this technology, all of these technologies really, IPS, IDS, Umbrella, AMP, all of those can be layered onto the SD-WAN solution now. Next up, we have the concept of application routing. We talked about this a little bit earlier, and we related it back to the idea that we can do per app policies as traffic comes into our routers. So we think about the idea that maybe email traffic shows up on this router, and we might want it to be treated a particular way. Let's say we want that to use our internet circuit. We want to conserve bandwidth on our MPLS, which maybe we'll just say this one on the left is MPLS. And as such, we're going to send email traffic across the internet. And likewise, we have voice over IP traffic coming in. Well, that's very mission critical traffic, and so we're going to send that out our MPLS circuit by default. But in either case, if we have quality issues out the internet link or possibly even out the MPLS link, we can swing those applications over to the other circuits in those situations. Next, we have a really cool feature that's all about cloud optimization. Now, if you're like me, when I first learned about this, you're sitting there thinking, all right, Jeff, SD-WAN, cloud optimization, like how is SD-WAN going to optimize my cloud environment? And we actually have two different options for this. First of all, we have this concept of on-ramp for IaaS. IaaS stands for Infrastructure as a Service, and it's when we run virtual machines inside of a cloud space. So in our case with SD-WAN, what we're going to be looking at is the ability to deploy a virtual router into either Amazon Web Services or Microsoft Azure. These are two of the most popular worldwide platforms, and so those are the two that are supported, at least at the time of this video. But by the time that you're doing your SD-WAN designs, you might want to double check and make sure that your your public cloud provider is supported. But the idea here is that we're going to use vManage to automatically provision virtual routers into our cloud space. We don't have to go through the trouble of doing it ourselves. We can simply click a button inside of vManage and it will push that router out and optimize our networks for us in the cloud. That allows our cloud virtual machines to leverage the SD-WAN infrastructure. So we have a virtual router now in the cloud space with all of our virtual machines attached to it, and now we can bring that into our different WAN circuits. Maybe it's internet-based, maybe it's MPLS-based. Our cloud services can support a variety of different WAN circuits, and this is one way that we can take advantage of SD-WAN in the cloud space. Now the other option besides on-ramp for IaaS would sound similar, but it's on-ramp for software as a service. That would be SaaS or SaaS. Software as a service is, we're not running virtual machines anymore. We are simply consuming a software package that you're running in your cloud space. And now we're thinking, okay, again, how do I optimize SaaS using my SD-WAN provider? Well, the way we do that is this. Let's take an example where I have an internet circuit at this location down at the bottom, and maybe up here in the green space, I have another internet circuit. Now I get traffic into this router on the bottom that is destined for my cloud provider. Which internet circuit should I use? Because we might look at this and say, well, we should just use the local internet circuit, right? I mean, that's going to be the best path. But when we look at worldwide networks, we might have a really fast connection through the MPLS cloud to the other site. And so it's possible that this internet circuit is actually the right place for us to exit our network and go out towards our SaaS provider. So we're going to be monitoring this and taking the latency of the WAN into account. We're going to be able to figure out the best internet path for getting out to that particular SaaS provider. So these are the ways that we can optimize our cloud environment. Again, I wouldn't necessarily look at SD-WAN as a way to optimize cloud, and yet we see two very clear ways that it can improve the way that we utilize cloud and the way that we access it. Now, the last component we're going to discuss would be vAnalytics. vAnalytics is an optional module, and it does require an additional license from Cisco. It doesn't come included in an SD-WAN solution. In fact, a few of these features are that way, so we need to be careful with our designs when it comes to planning on using any of these features. But either way, vAnalytics is going to provide us deep insights into what's happening in our SD-WAN space. Specifically, we're going to be looking at utilization trends, capacity projections, application quality, all of these things that SD-WAN is handling for us. But to be able to provide insights based on that data does take a little bit of extra work, and that's what vAnalytics is going to provide. Furthermore, it's going to give us a dashboard that gives us very clean access to all of this data. And the dashboard is going to be broken down into things like network health, network availability, and application quality. And so at a glance, we can use vAnalytics to give us a better idea of what's happening inside of the SD-WAN space. So as we zoom out from this, we do want to understand exactly what all of these different features do. For example, automatic onboarding and security and such. We need to understand and have a grasp of why we'd want to deploy SD-WAN. There are a lot of features and benefits to deploying SD-WAN beyond everything else we've talked about with the control plane and the data plane and the management plane and orchestration plane. Those are how it works, but this is really part of why we'd want to deploy SD-WAN into our network space. And second of all, keep in mind that some of these features do require licenses, so we can't make the assumption we're going to have all of these. For example, Cloud On-Ramp and vAnalytics for sure are going to require an additional license. But we need to talk to our Cisco reps or potentially Cisco partners to make sure that we're getting the licenses that we need in order to run the features that we desire. I hope this has been informative for you. I'd like to thank you for viewing. We have reached the end of yet another skill on our ENSLD journey. So let's celebrate that by taking this quiz. First up, out of 5 questions, what tunnel types can be used at the SD-WAN data plane? Well, we have 2 different choices that we can use at the data plane for our tunnels. We're not going to rely on VXLAN or Lisp. Those are for SD access, not SD-WAN. And similarly, IP and IP is not going to be very helpful for us. Instead, for the most part, we're going to build our tunnels on IPsec. However, Cisco does give us the ability to deploy on GRE if we so desire, even though that's not going to give us traffic encryption. Next up, what routing protocol is used to share routes across the SD-WAN environment? Well, we're not going to do traditional routing between the edge devices in our infrastructure. So we're not going to be running BGP or EIGRP or OSPF. That's how we ran traditional WAN infrastructures. Instead, we're going to use OMP, the Overlay Management Protocol. It's a BGP-like protocol in that we're exchanging routes and attributes that give us a whole lot more control over the routing in our infrastructure. Third question, how are netconf and REST leveraged in the SD-WAN management plane? So here's the deal. We have vManage, which kind of looks like this. It looks like a resource tree, I suppose. And we as the network admins are going to be logging into vManage and leveraging it in some fashion. And then vManage is going to push those policies down to the vSmart and to all of the edge devices. So these would be our routers. So we have two different protocols at play here. We have netconf and REST. And what we're going to find is that we can leverage REST APIs as the user, as the admins, logging into vManage. We can use the GUI, but even the GUI is using the REST APIs on the back end, and as such, regardless of how we access vManage, REST APIs are going to be at play. Now on the back end, when we're reaching out to the devices, this is where netconf comes into play. Netconf is a protocol that securely and programmatically configures routers in a way that's superior to potentially logging in to CLI like we used to do. So when we look at our answer choices here, netconf is going to be used between vManage and edges, so that would be A as an answer, and REST is going to be leveraged by us, the network admins, logging into vManage, and so D would be the answer there. So A and D are our answers. Question 4. Which device must be deployed with a public IP address or otherwise be behind one-to-one NAT? Well, there's only one device that absolutely has these requirements, and that's going to be the vBond controller, which is part of the orchestration plane. Remember that the reason for this is because of that concept of NAT traversal. If our vBond is going to support NAT traversal, in other words, helping our edge devices communicate to one another when they're behind NAT, then it has to be accessible outside of the NAT domain. And as such, we either need to give it a public IP address natively, or we can put it behind NAT, but it has to be one-to-one. In that sense, it still does have a public IP address assigned to it. And last question, what information is carried within a transport locator or a TLOC? Remember, a TLOC is essentially a three-tuple of information. We can't even equate a TLOC to a physical or logical IP address on a device. Instead, we're going to use the TLOCs as a connection point, and then we're going to leverage OMP to tell us how to get to that connection point. So as a descriptor of a connection point, we're going to use this three-tuple of information, and that three-tuple of information consists of A, the system IP address, C, the color, which would describe our WAN circuit, and D, the encapsulation type, IPsec or GRE. We are not carrying VPN ID, okay, but the thing we might expect a TLOC to carry would be a routable IP address, a way to get to it. And the TLOC does not natively carry that information, so B is not an answer. So A, C, and D, those are our answer choices for this question. Well, that wraps up this quiz. If you find yourself missing any of these key points of information, then be sure to go back and watch the appropriate videos in order to make sure you have all of those down. Otherwise, congratulations on completing Describe Cisco SD-WAN architecture. I hope this has been informative for you, and I'd like to thank you for viewing.